Welcome to After Hours Engineering, episode 17. In the previous episode, we finished the simulations and tested the water of synthesis with a few fun examples. As mentioned previously, we need to move data into and out of our FPGA in order to communicate with our processor. Granted, we haven't synthesized yet, and we will. We still need a way to communicate, and as such, we're going to look at two forms of communication, SPI and UART, and how we can connect them via a very, very simple bus, nothing on the order of AXI. So in this episode, we'll look at the very first one, which is the slightly more complicated and challenging one, SPI protocol. So, let's go! First and foremost, SPI is very much a device-centric protocol. Masters can be anything from microcontrollers to mainframes. But slaves are almost exclusively physical devices, which means it's extremely rare that the slave changes its behavior while operating. For example, it won't spontaneously change from an I/O expander into a TFT display. Now this also means the specs you read describe precisely how to interact with the slave device. Some slave devices are full duplex all the time, for example a temperature sensor, while others are not, like the MCP23S17 I/O expander. SPI has 4 modes labeled 0 through 3. And the differences are based on the polarity of the clock and the phase of the data. Other than that, they are identical. The concept is exactly the same, moving data based on the clock. There's no difference between the chip selects in all 4 modes. In this episode, we focus on mode 0, and as such, the data needs to be set up prior to the rising edge of the clock and changed or set up again at the falling edge of the clock. The slave will act exactly the same way. You need to have your slave in the same mode that your master is in. Also, the clock itself is ultimately in control when it comes to transferring data. No data is transferred as long as the clock is idling, and in mode 0, idling is low. So if you wanted to send 2 bytes and get another byte back in 3 years' time, just send 8 clocks, stall for a year, send 8 more clocks, idle for a year, and then send 8 more clocks, and you'll get your data back, as long as the device hasn't died by then, in 3 years. Of course, that's unrealistic. Normally, this is usually 2 or 3 clock cycles, depending on the device. The device will tell you how long you need to wait between bytes or bits, or whatever the case might be. Some devices require 16 bits all at once. Again, it always comes down to the device, and the device will give you specs that say exactly how to control it. So the chip select is independent of the mode as well, and it needs to be asserted prior to the first rising edge of the clock and held there according to the device's specification. The device may say you need to raise and lower the chip select on every byte. It may say you can keep it low for the entire transfer of hundreds and hundreds of bytes, kilobytes, megabytes of data. It again depends on the device itself. If you're going to transmit data to the slave, you set up each one of your bits on the rising edge and then shift them out on the master out slave in pin. And the slave will do the same thing. It will shift its data out 1 bit at a time and route it to whoever is listening. In this case, it would be the master, so it would be master in, slave out. So this is mode 0. The key points here is that the clock is ultimately in control of the transfer of data. Without clocks, you'll get nothing from the device. The device will just sit there and twiddle its thumbs forever. Also, the phase of the data and the clock are important, at least depending on what mode you are. You don't want to set your data up on the rising edge, or you'll violate timing constraints for sure. I mean, that's generic with any kind of digital circuit, is you always want to set your data up prior to the rising edge. And we're going to see how we do that in both the master and the slave in System Verilog. So there you go. This is mode 0 SPI. It's technically not that complicated. It's simply a clock, a chip select, and then shifting data out on the correct rising and falling edge of the clock. That's it. Remember in the previous episode we touched on clock domains where I mistakenly mixed unrelated asynchronous signals? Well, here we are. Let's review it real quick. We had our softcore processor domain right here and our interrupts coming in from some unknown device, or in this case my simulation. I had mistakenly sent the interrupt signal directly to the clock domain or the CPU domain, and that was causing problems. So what we did to fix it was we used a 1-bit FIFO. We sent a signal this way, the CPU recognized it, and then sent a signal in the other direction. And that's what solved our problem. This is commonly called CDC, or cross-domain crossing. We need to handle the same situation, but this time we'll use a different approach, namely a 2 flip-flop synchronizer. And there are many ways to approach this, and each one is specific to a use case. In our case, the 2FF works great. So how does that work? Well, here's some sample Verilog code and a potential, or in this case, an exact replication of this Verilog. You have your sporadic asynchronous signal coming in over here, and you need to synchronize it with the destination domain. One way to do this is to run it through 2 flip-flops that are synchronized to the system clock of the receiving domain. And out comes a synchronized signal. There are limits to this, limitations, but in general for lower clock frequencies or very simple signals, this will work great. In more complex scenarios, you might need to use a full-fledged FIFO in this case. The parts up here in yellow are optional, and they will be used for SPI in our case for detecting the rising and falling edge. And again, they're using the synchronized signal so that we're getting synchronized falling and rising edges as well. This circuit actually works very well, and we'll see it in use in the SPI example. Before we implement an HDL version of SPI, let's make sure we understand how to use SPI. And I've chosen to use a Pico RP2040 as the master and an MCP2317 as the slave. So over here is our circuit diagram that represents what you're seeing in the upper right hand corner of the display here. Over to the left is the probe, and we can pretty much ignore that because I've already uploaded the code over to the master, the Pico that is acting as the master. And as such, we can ignore these wires, and these. However, we'll focus on these wires. This is an interrupt. I'll show you the code how I set this pin up to act as an interrupt sensor. So when the MCP senses some sort of activity on our bus over here, it sends an interrupt down the wire and triggers our Pico to do something. The master is over here on these 4 pins. We have our slave in, or master out, slave in, and we have our master in, slave out. So the slave is going to send data down this wire and over to our master here. Then we have our chip select right here and our clock. Now, one thing to notice in this circuit is that the MCP can operate off of a moderately wide range of voltages. And I've hooked up the 3-volt line power rail up to the MCP so that it operates in 3.3 volt mode. I do this because we are actually taking a pin from the MCP and routing it back to the Pico. And a Pico is not 5 volt tolerant on its I/O lines. That's okay, we can run the MCP in 3.3 volt logic levels. So, having said that, when we send commands over to the MCP, it's going to configure it for one thing. We're going to do some configuration, but we can also send commands to read pins on this. And one of the pins that we're going to read is GPA1, and another one we're going to turn on and off a LED by setting this value in the register to 0 or 1. So let's take a look at the code to implement this. It's fairly simple. It's a fair amount of code, but it's not that much to begin with. So we start up here at the top. I've defined a variable here to represent our pin that we're going to sense an interrupt on. And then I have a callback that'll recognize that interrupt. And this is one of the callbacks that we're going to actually use. So let's come down here. This is the main program itself. We do some usual setting up of the Pico itself. This is special. We're setting up the SPI and we're initializing it at 1 megahertz. The MCP can operate at 10 megahertz. We're setting up some more pins for the clock and the transmit and receive, and then the chip select will be on its own line, manually controlled by the program. Then we'll set up our clock to idle low, and finally we'll sleep a few just to give time for the system to come up. The next part we do is configuring the MCP itself. Now I could bring up the diagram of the manual on it, and it would tell us a whole lot of things of what we need to do. One of those is reading all of these registers right here. This is all of the registers and bits that we need to set or clear, and values that we'll send into them. Now I'm not going to go into depth. The MCP is a bit complicated, but it isn't really part of this exercise. So ultimately what we do is we set up each one of the registries. We set up the control registry, which direction we want that bit to go into, how we want to compare for a change so that when I push this button it's going to toggle this line. The MCP will recognize that as a change and then send out an interrupt. And then finally we set up our pin to recognize our falling edge of an interrupt. So our MCP, this pin will stay high and it'll drop low when it wants to interrupt our Pico. And of course go into a loop sensing when an interrupt has occurred, and if it has, we pulse the lead and then we clear the interrupt flag. If you don't read this register here in the MCP, it will never trigger an interrupt again. You have to respond to the MCP saying, hey, I got your interrupt. And you do that by literally reading the interrupt register. And that's it. So now let's take a look at pushing this button and see if it works. So I've already uploaded the code as usual. So I'll come over here right there, and you can see that it's interrupting our code. Excellent. In addition, I went ahead and captured some of the signaling information moving back and forth between the Pico and the MCP. In this particular instance, we're sending the 41 command. So if we scroll down here, you can see that the command is 41. This is the read, RD. And then we tell it what we want to read, which register we want to read from. And in this case, I've configured the MCP for bank 0 operation, address operation. So E means that I'm trying to read the interrupt flag status to find out if it was set correctly. And I get a 1 back, which is correct. I did set the 1-bit flag on the interrupt register. We can also take a look at writing to one of the registries. So the opcode for that is 40, so there it is marked in our header file, 40. And what register do we want to read? That's the second byte right here, and that's the A. So here we're reading the IO control register to find out what value it has, and it's responded with the 20. So you can see that this is SPI. We're talking to the device, and the device is responding. The specification says that we always pass in a opcode and then an address, and it will respond with a value. Now this is half duplex mode because a temperature sensor, for example, may have actually started sending data back on the MISO line right here. Even as we're sending commands and various things, a temperature sensor can constantly send data back. However, the MCP is a half duplex type of device. It only responds after you've told it what opcode and what address to deal with. And that's what you have here. So this is SPI. Now that we have a better understanding of the SPI protocol and how to use it, we can code an HDL version. We'll build a SPI slave first based on the layout diagram we're looking at now. We'll have a mini-com program looking at the keys 9, A, or B. They'll transmit through the UART to the Pico. The Pico will turn around and send a 3-byte sequence based on what characters they touched, and it will send it over the SPI protocol. We'll have synchronizers running on both sides for signals that are coming in across clock domains. The BlackiceEdge will then run its module that is looking for the first 2 bytes and respond with a 3rd byte over the MISO line back to the Pico. In the meantime, we'll be capturing the signals on the logic analyzer and showing them on the display. Our HDL code is mainly 4 files: the top, the slave, the synchronizer, and the parallel load shift register. We'll look at the top first as usual. We have our clock, which is in 25 megahertz. We have an LED. The blade isn't used anymore. We replaced it with the LA, the logic analyzer. It wasn't really providing enough information. We exposed the pins to the Pico so that we can transmit data to and from the Pico. Our counters as usual, and then the slave device itself. We route all of our signals into it. So let's take a look at the slave. It's the biggest of the modules, of course. The very first thing is we're maintaining a state, and we are looking at receiving a byte in. We need to synchronize on the 3 signals coming in from the Pico, and so I set up 3 synchronizers, which we'll look at in a minute. We've already talked about them in general, and that's one for the clock itself, the master out, slave in, and the chip select coming in. From there, we need our parallel load shift register to send data out back to the master, and we have some state variables for detecting where we are along in the signal in the protocol. For example, we need to know when the final fall state is so we know where to go at the end of a transmission. So we'll start here up at the top. Our slave is driven off of a single clock, and I use the high speed or the higher clock frequency, and I think a lot of designs do this, where they'll use this high frequency clock to provide enough time to set up the data that's going to be sent back to the master, and I'll show you that in a second. So we detect the falling edge on the chip select, and that starts the ball rolling. We clear out some buffers with some values in them. In a more advanced slave, you would probably want to have something way more advanced than just filling this out with FFs, because that leaves out the fact that you could actually use FFs. And then we set our first state to idle. So the slave will come up and start idling as soon as the chip select comes in from the master. On the first falling edge, or on any falling edge for that matter, and that we're in the transmit mode, we're going to enable shifts so that we can set up a bit to shift out of the shift register and before the rising edge of the clock, because here we are on the falling edge of the clock, and then we will switch over to the shift stage to allow that bit to be shifted, and then turn around and immediately go right back to the transmit stage. So on the rising edge of the clock, we look at, depending on the state, if we're idling, we immediately go to transmit. Remember, this is the rising edge of the SPI clock, and on the first one we're going to almost certainly go right into transmit. If we're in transmit, we're going to determine what bit we're on, and when we finally hit the last bit, we'll go right back to idle. And that's it. This thing goes from transmit to idle, and it'll just sit there and idle and idle and idle if no bits are coming or going. And of course, we're grabbing the bits that are coming in, the synchronized version of it, and storing it in our receive byte. Now, a lot of the remaining code is really just the implementation of the device itself. This isn't really part of SPI. This is just this slave pretending to be an MCP 2317. And in order to do that, it needs to look at the patterns that are coming in and then capture them and store them into registers. If we are on a state load, we're going to go back to idle and clear out our buffers. At the final end of the whole entire byte sequence, we're going to take that received byte and put it in our buffer and then bump the buffer up. This allows us to see multiple bytes at a time instead of every single byte. And then once we've reached the end, we reset that count. So as the buffer is filling up with bytes that are coming in, our pattern selectors, which we're going to look down here below, right here, will come down right here. This is our pattern selectors. Again, this has nothing to do with the slave. This is just the device. All this is pretty much just the device trying to figure out what byte patterns came in. If it's a 41 and an A, then we're going to send out a 28 back to the master. And a 41 OF will send out an F9, and if it's a 00, we'll send out an E4. And that's how this thing works. We do have one more module in here, and that's our 8 input multiplexer. And that allows us to route one of the responses back to data out. If we come up here to data out, you'll see that it's been attached to our parallel load shift register. And that's the slave module. It's really not that complicated in terms of transmitting. The trickier part was preparing the data before each one of the rising edges of the clock. You want to do that on the falling edge, and that's where this is right here. This is activating the shift register, but it's doing it at the high frequency. It's not doing it at the SPI clock, it's doing it at the high frequency. But these falling edges and rising edges, they are operating off of the clock coming in. So that's the real big key with this slave, and we'll see that in the timing diagrams when we take a look. Here's the synchronizer that we covered earlier. It's a 2FF right here. It's nothing more than this little tiny circuit right here, and it will synchronize the circuits and generate a rising and a fall all at the same time. And then our parallel load shift register, that was the diagram here, over here to the right, where we look to see whether we're resetting, we're loading, or we are shifting. And that's it. That's the whole entire slave module and top module all in one shot. It's a lot, I admit it, and the slave is the biggest of the lot. But we'll go through the timing diagram and check this out. Let's take a look at a high-level overview of the SPI Slave device and its timing diagram. So what we have here is our system clock on the slave and the SPI clock, the synchronous version. We're detecting our rise and fall of the SPI clock itself. We'll need that information. We also have the chip select that's coming in and the synchronous version. We have the data that's going out and the data that's coming in. So the way my specific slave works is that I operate off of the higher frequency clock, and this allows me to do work in between the SPI clock itself. So for example, the chip select comes in. As soon as it does, I prepare that parallel load shift register with the data that we're going to transmit out, and it also presents the first bit before the rising edge. That's the key. So for each one of these edges right here, we're sending out a 2.8. So if we look at the upper top here, you can see that the master has received the 2.8. On the rising edge, we have a 0, 0, 1, 0, that's a number 2, and then a 1, 0, 0, 0, and that's an 8. So that's what we're actually sending out. Excellent. And we're receiving down here at the bottom the byte that came in from the master, which is a 4, 1. So this is all working as correct. You can see that on the falling edge, I do a little bit of extra work to set up and shift the parallel register for the next rising edge. And that's exactly how this works. Okay, we're finally ready for the synthesis of our SPI Slave. I've already uploaded it to the BlackiceEdge, and I've uploaded the controller code, the master, to the Pico. So we're ready to go. I'm going to start up the Minicom program right here and bring it up. There it is. Now when I hit the number 9 key, that should send 2 bytes out to the FPGA, and it should respond with another byte. In this case, we should get 28 back. We'll know both in the diagram in the logic analyzer, and we should also see it appear in our terminal. That has to be in both places. One, the logic diagram is only showing us what we're seeing coming out of the FPGA, but the master on the RP40 needs to also recognize that the timing needs to be correct. So let's see if that's the case. So I'll come over here and start the logic analyzer, waiting for data to come in. I'm going to hit the number 9, and sure enough, we have got the 28 back. Excellent. You can see that the first 2 are zeros because our FPGA isn't just blindly sending data back. It actually is sending data, but it's sending nothing. And if we look at the timing diagram, we also see the 28 as the second byte. We also sent that 41 and a 0A. So it recognized these 2 bytes and sent us a response in return, the 28. Awesome. Now let's see if it can do 2 more. We're going to hit the A key, and that'll transmit a 41 and an F, a different pattern. And the slave should recognize that and send us an F9 back. So let me start the logic analyzer back up. We'll hit the A key, and there it goes. We have got an F9 back. Excellent. So our slave module on the FPGA is definitely working. It's recognizing unique patterns coming in from the SPI protocol and responding equally with the SPI protocol back to the slave. We'll try one more here. The B key will transmit a 441 in hex and a 00. We should get an E4 if it recognizes that pattern correctly. So I'll start the logic analyzer back up. Here we go. And I'm going to hit the B key. And yes, we got an E4 back. Excellent. There it is right there. We sent a 41 and a 0, and we got an E4 back. Nice. Things are working exactly as we expected. We have succeeded in creating a SPI module using synchronizers between two unique domains and a parallel load shift register. Awesome. Well, that takes care of one half of the SPI protocol, but what about the master? No worries, we'll cover that later on in this series, where we'll connect several slave devices to our FPGA via an advanced interrupt controller, and by advanced I mean a moderately advanced one, a PLIC, a platform level interrupt controller. So in the next episode we'll look at UART and how we can talk directly to our FPGA via Minicom. Exciting things are in the works, so until next time, peace.